purpose of this podcast is to advocate, learn, and continue the journey for truth. Welcome to the In Bad Faith podcast. Could you quickly give us a bio and your background as an expert in facial recognition software and technology?
Yeah, so I'm currently I'm a professor and the program director of computer science for Milwaukee School of Engineering. And our program here focuses on artificial intelligence, deep learning, machine learning, and data science. So I teach courses in all those areas. My PhD is actually in computer science. I got that from Vanderbilt in 2009. I worked in computational modeling and high performance computing then. And so since 2009, the whole revolution in deep learning has really happened. And that's really what has enabled these the new technologies in facial recognition, computer vision to really reach out farther into our society than they ever have at an accelerating rate. And so so I've been working on projects, research projects, student projects in this area for a number of years now. So
that's great. Could you, if you wouldn't mind, for the people at home that don't know what deep learning is, could you expand on that a little bit?
Absolutely, yeah. So deep learning is a branch of artificial intelligence that essentially uses, at its core, what are called artificial neural networks. Artificial neural networks are really mathematical representations of things that might exist in the real world. They're really kind of loosely based on the concept of neurons in our brain and in their animals and plants. And the idea is these artificial neurons are mathematical representations that sort of approximate the behavior that we might see in biology. And the way that we approximate the behavior is by showing it lots of examples. So there are a lot of analogs between AI and deep learning and the real world. So for example, the way that, a toddler might learn, whether an object is a square or a circle is by showing them lots of objects and reinforcing the behavior. So, they point at an object or they try to jam it into a circle hole and it doesn't fit. And all those experiences train their neurology for them to have kind of build these higher level understandings of what things are. We do the same thing with deep neural networks, but the training phase is much easier to control in these systems. So what we do is we use large data sets of examples. And if we're doing a computer vision task, it's images. We can do signal processing tasks. So it could be like ECG signals from a cardiologist. It could be audio signals from a microphone. Those can all be used as training data that can be used to train these deep neural networks. The reason they're called deep neural networks is because they have lots and lots of complex layers that sort of help the decisions become higher and higher level. So 10, 15 years ago, the decisions that neural networks could make were relatively limited because the networks weren't very deep. And it was really because we didn't have enough data, we didn't have enough computational power. And so we could really only make limited, reasoning and judgment systems.
Would that be like circles to triangles and basic stuff, and then the technology moved to more advanced patterns and...
Exactly. Yeah. And in fact, one of the early kind of computer vision tasks that happened, and this actually happened in the 90s, came from the US Postal Service. So if you can imagine, the number of letters that have to go through the Postal Service for them to figure out where they go, they really want to have what's called optical character recognition technology. They want to be able to say, okay, this is a 6 when they see it, and they don't want to have a human do that judgment call.
Makes sense.
So in the 90s, they started pursuing projects using more classical machine learning approaches to be able to do optical character recognition and recognize handwritten digits. And they were successful. It took a lot of effort. There were a lot of engineers that worked a long time to be able to build a system that was automated, that could recognize those handwritten digits. Now we do this in an undergraduate classroom in a matter of minutes. It's really easy to train these things with deep neural networks, and it takes very little effort because the software is matured, the data sets have matured, these models have matured to the point where it's really a solved problem. And now what we can do is, instead of recognizing just handwritten digits, we can actually take the next step and start recognizing words and phrases in kind of the realm that we call natural language processing, where we're looking for higher and higher levels of abstractions and concepts. And these deep learning models can, in many cases, learn these higher levels of abstraction. So we're not just learning these little nuanced details, it's these bigger concepts that they can intuit.
Oh, thank you. Thank you. I have a little experience. I did some work with Google Korea, and I was working with their English department. And the way it was described to me is the gentleman was saying, I'm chopping up sentences. And so that's kind of what you're saying is like you're taking little bits and identifying them and then making patterns.
Exactly. Yeah. And that's, that comes straight out of, this field of natural language processing where we tokenize pieces. And then, you're looking for context between the pieces, right? So one of my favorite phrases from this is fruit flies like a banana, which out of context, you can't tell whether it means that there's, a yellow, fruit flying through the air, or if you're talking about little insects that like the banana. So there's all these complexities to language that require a lot of sophistication in these models that can interpret what's going on. And then, from that, you can do translations, right? Or you can do annotations if you're taking, spoken language and putting it into Word or vice versa. And we've gotten to the point now that real-time language translation is possible. So we can speak in English and in real time translate that to a number of different languages. That's really just happened in the last couple of years.
I think I've seen some products.
Even 5 years ago.
Products that are out there available.
Yep. Yeah. And the time from sort of a research hypothesis to collecting the data set to having a product out there that's successful in this is getting shorter and shorter for a lot of these domains.
Great. I'm going to bounce around here. Maybe the questions don't necessarily have a chronology. One of the things that I'm interested in is using the technology to find people who we're looking for, whether that's missing people, et cetera. So what about missing persons? Can facial recognition be used to find missing or wanted persons? I know that at a basic level, we all kind of understand that that's possible. I was told that some people are even unidentified or have been identified at sporting events. Sure. Is there a legitimacy to this, or is that kind of a one-off that it would just it was an accident?
It definitely is possible. And it boils down to a couple of things. So when we're training these deep learning models, we train them for a specific purpose. So we can't take one model that's trained to, interpret natural language and then just redeploy it and have it be able to do facial recognition. But you actually can take a model that's designed to do facial recognition, and maybe it goes from emotion recognition to, where it's trying to say, okay, this person is happy or sad, and sort of has benign applications. Maybe in advertising, if they have a video feed in a stadium, they're trying to make sure that, people are, they're marketing the right products based on their mood. You can actually, with the right data sets, redeploy that model using a technique called transfer learning and actually have it do different tasks. So instead of doing emotion recognition, you could potentially do individual recognition. So you could say, okay, if you know that an individual, that this is a picture of Susie and this is a picture of Bob, you can actually redeploy that emotion model to be able to identify individuals. Now, it may or may not be accurate in doing that. You have to have pretty significant training sets to be able to train models to be effective at that. However, there are some techniques that are making it possible so that you can use smaller and smaller data sets to find specific people. So for example, if there's a wanted individual out there and there are a handful of pictures of that person, those pictures might be sufficient to be able to identify somebody in a large crowd. There are limitations to all of this, and it's worth talking about those limitations. If the pictures you're trying to, find, you see these on the news, right? There's this grainy photo from the middle of the night of an individual, often there's not enough data in a really grainy photo or a black and white photo to be able to do general recognition. There are techniques with image enhancement and that kind of thing that can be done, but there are limits to that. And then, there are also limits to the technology of, potentially in the stadium, right? If the stadium, you're trying to recognize people and, the camera just doesn't have enough resolution to do that. That also can be a limiting factor. So sort of all the stars have to align to make that work. But, from a technology standpoint, systems like that can exist and do exist. So yeah, it's just a matter of how they're being deployed and what the intention is behind their deployment.
I think it's coming clearer, and you did kind of hit one of the things I wanted to mention was about the limitations of the technology. So thanks for hitting that. I think that oftentimes we look at issues not necessarily through their limitations, and I like that as a place to start. So thank you so much for hitting that. What about plastic surgery? Can you trick this? Could I easily trick facial recognition with some plastic surgery?
Yeah, although I would say that plastic surgery is an extreme way to trick it. There are actually already products in the market that you can wear on yourself one of them is relatively simple. You can put a face mask on. And if your data set is not sufficient to recognize you with your face mask on, it's really not going to work. You can think about like, if you put a motorcycle helmet on yourself and it's a shaded visor, there's no way to recognize the individual that's there. So there are sort of variations on that can be used to more or less, get around the technology or fool the technology or whatever you want to call it. But, there's still analogs to what would have been done in, non-machine learning worlds or non-deep learning worlds where, if somebody wants to hide their identity, a bank robber, what do? They put on a ski mask. They're,
and that's not new, right?
It's not really new, right? But, the difference with deep learning technologies, you don't have a person watching the video feed looking for the bank robbers or trying to see that little detail. You have systems that are massively scalable and capable and can watch every frame and every little detail that can be processed. So their ability to look at things massively parallel is much broader, and so scaling them gives them a lot of their new capabilities, but they can still be defeated by relatively simple means.
Relatively simple. I think that's an important point that you deliver there, that it could be avoided for people that are trying to not be identified, right? So
absolutely, and you can look at in the Hong Kong protests and lots of other areas around the world where there's unrest and there's simultaneously concern around surveillance. Often they're going to be, the protesters will wear facial coverings and other things to try to hide their identity, and I think those can still be quite effective methods.
One of the things that I just kind of thought about as we're talking here is the face masks and COVID-19 and more people not, and that's being a big boundary for, facial recognition development. Is that going to have an effect long term? And I guess I think if everyone's wearing a mask, is the technology going to start focusing more on eyes and ears? Something like that, right?
In theory, it could, right? And I think it's kind of, where our society goes with this remains to be seen. I think, with less information, so hiding kind of the lower part of your face, and not only that, but hiding it in varied ways, right? There's all sorts of different kinds of masks. That creates extra complexity. I mean, we've all experienced this. Any of us who've been on a Zoom call where you're trying to, or talking to another individual as a mask on, you're trying to interpret emotions when you can't see the lower half of the face. It's a lot harder. There's just less information. And the algorithms struggle the same way. They're able to pick up on, more examples and more nuances and that sort of thing. But to do that, they need more data. So there's sort of this pairing between, are they able to do this? And the answer is yes, but to a limited extent. And, the less data that they have to gather, so the less and less of the face that can be seen, the more examples it needs to see to be able to see the distinctions between the individuals.
So it's going to pinch the technology
at some point.
Yeah, I would but it's like pinches the technology where it's going to force it to learn a different method, right? By putting masks on, it's going to force the AI, if we get there, to, adapt and actually, so it's going to have a repercussion.
Absolutely. Although I think it's worth noting, the way these technologies work is they primarily are what are deemed sort of offline training systems. So the idea is data is collected, That data then is used to train the model, and then the model's deployed. So they're not really an online learning system where, let's say you go to an airport. Just because today there are more people wearing masks in an airport doesn't mean that those tools are working any different than they were, in days when there weren't masks. It may mean that they're less effective now because the models that are being used were trained when people didn't have masks, and now that people have masks, they look different. A lot like if the lighting conditions vastly change, the models may or may not adapt to that new environment well. It's unusual to find online learning systems where they're adapting on the fly, because there can be all sorts of problems and security exploits that can happen with that. Microsoft released a chatbot called Tay. This was a number of years ago. That was an online learning system. It essentially took in information from primarily Twitter and other online sources, and then became its own chatbot and had developed its own personality. A bunch of people figured out that they could feed it terrible things, and it quickly became racist and homophobic, and they took it down within a matter of hours. It was a good example of why well-intentioned technology can be exploited rather quickly. And so online learning systems tend to be unusual in this space.
That's good. That's actually one of my questions, one of the perceived dangers. So I think you kind of hit that too. The name of the podcast is In Bad Faith. So we kind of focus on, what could a bad faith actor do with this technology?
Yeah, and I think, there are a number of different potential exploits that can exist with deep learning models. But if a system is engineered around them properly, it is less likely to be exploited. So here's an example. So my car has a camera in it that, faces out the dashboard, and it's connected to the cruise control system in the car. And so it's vision guided cruise control. I was warned through actually an online forum that one of the early versions of the deep learning model that's in the car didn't recognize a certain type of taillight. So there's some, most taillights on vehicles are two independent red blobs, right? But there are some vehicles that actually have a red connector that go between those two independent blobs. And the vision system didn't recognize taillights that looked like that because it was never trained, evidently, with taillights that looked like that. And so I was warned that, you can trust the system, but you can also run into a situation where you literally run into the car in front of you because the car doesn't see it. So you have to have a modicum of trust that's built in and understand what the limitations are. If we're looking at in bad faith, if you knew that exploit existed, you could modify the taillights on your automobile to try to take advantage of vehicles that are behind you and cause an accident, right? And there have been research studies that have shown that you could do something as simple as putting stickers in the middle of the road to convince automobiles that are using self-guided driving based on computer vision systems that lane is ending. And actually, at highway speeds, one of the decisions that a car can make is if it thinks the lane is ending and it doesn't have space to brake, it will merge. And so that can cause all sorts of emergency braking situations just from somebody putting some stickers in the middle of a road. So, understanding the limitations, the challenges that can exist in these systems, they can be exploited. There's no question. It has to be an iterative process. It's not like we're going to develop one of these systems, expect it to work flawlessly, and then all world problems will be solved. It's an engineering process. We need to go back, refine the systems, understand our test cases, and continually examine what the limits are of these tools.
Great. I think I really answered the question. I just want to peer over at see what I can hit here while we have limited time. What about identifying a John or Jane Doe?
Yeah, so I think it's definitely possible. I mean, I think one of the things that comes with this technology is, if you imagine an investigation where you're trying to find a missing person, and a lot of times there are cameras that have been deployed, around the world we live in, and understanding and processing all of that data becomes intractable for humans. There's too much video feed. You can imagine if you drive through any major downtown, you might be captured by literally 1,000 cameras.
Wow.
And so if you want to track, if somebody wants to track your movements, the number of people that would have to be involved in, watching every video and time syncing all the videos, like it's too complex. It's too hard of a problem for people to solve. But it's an ideal problem for a computing system to solve. And so there are actually systems out there that are designed, to do analysis of multiple streams of video that are captured simultaneously and synchronize that analysis. And they can be done, so you can use that to identify missing persons, to, track movements through the city. But, that can be used for good. That can also be used in other ways. And, how it's used is really what matters. The reality is the technology exists. We benefit here in the US somewhat because a lot of our systems of cameras are not hooked up together. They're often, private companies and ATMs and individuals that all have their own cameras. And so there's not this like web of systems that can all be simultaneously analyzed by Big Brother.
Skynet type.
Yeah, but those systems do exist in other countries. The city of London is a good example of that. They have, I think it's like one security camera for every 2 people or something like that in the city. It's a shocking number of cameras. There are plenty of other cities in the world that also have a pretty high saturation rate of cameras that are actually all networked together, where you're kind of centralizing all that information. And where you centralize information, that's where risk sort of comes in for misusing that information.
That's really interesting. I didn't realize that. I knew that London had an issue with the facial recognition. I didn't realize it's because they have their own central, where all the information is being fed in simultaneously, right? What about
there are a lot of really good use cases for it, and it was deployed for those positive use cases. And I think, I don't think we should be afraid of deploying technology because it has the potential to have bad uses. We just have to do it in responsible ways.
I think it's a really, really great point. And I think that, coming from someone you've explained it pretty clearly, the technology. I know that there's a lot of pushback, and there's going to be a lot of pushback, particularly on this video when I post it, where people are going to disagree with you and say that it is more dangerous. And I guess, like, if you could just maybe comment a little bit on that, because there's going to be pushback on what people will interpret of what you said.
Yeah, I think the key is when technologies are just deployed in this way, I think the key is transparency. I think any time when a major technology like this that has the potential for abuse and has the potential for impacting a large number of people is deployed, there really has to be an honest conversation where the people who are impacted by that really understand the implications of it. Because ultimately we all make decisions, right? Most of us have smartphones in our pocket, and we're comfortable with the fact that our movements are tracked constantly. And if need be, warrants can be issued to find our exact location at any given time. We accept that level of potential scrutiny because we do a cost-benefit analysis, and we say, look, being able to, text my significant other and remind them to pick up milk from the grocery store is worth it. That's a reasonable trade-off in privacy. Everybody's going to have a different comfort threshold with privacy and what they're willing to tolerate. But ultimately, we as a society, when we have tools like this that impact a society, have to come to an understanding of what's acceptable. And, it's going to be different for different areas of the country, different cities, different countries in general. And I think we're already seeing that. There's a pretty wide variety of deployments of these technologies because of that. I still think the key is making sure that the population is understanding and comfortable with that level of privacy and the potential for abuse.
Thank you. One more question before we wrap up, related to what you just explained, is that I read articles that the facial recognition software has a difficulty identifying people of different races or a darker complexion, and that some people were being falsely identified. And could you comment on that, or how can we fix that? And is there a future to that?
Yeah, no, I think this is a really important area to understand. And this is something we actually spend a lot of time with our students to understand. All data has bias. It is not really possible to have unbiased data. And so if you train your models with certain types of data, you're going to end up with bias in your data. So I live here in Wisconsin. Many of the startups who are doing self-driving technology are located in California and Texas and all those sorts of things. I don't expect a model that's trained in California on California roads to drive well in Wisconsin. So what you need to do is you need to understand where is your model, where's your deep learning model going to be used to ensure that it's going to be effective in that area. And that doesn't matter if you're developing a self-driving car, facial recognition technology, you're going to end up with models that don't work very effectively. A good example of this is Pokemon Go. A number of years ago when Pokemon Go was a big deal, I think that was like 4 or 5 years ago, there were some researchers looking at where do these Pokemon randomly show up. They're not random, they're actually generated by a machine learning model. And it turns out that machine learning model was biasing where they were showing up. They tended to show up in white affluent suburbs. They weren't showing up in more diverse areas. And it was exposed that the developers of the software used areas they were familiar with, and that population is biased in a certain way, and it caused the results of the algorithm to work in a certain way. Once that was exposed, they understood, okay, we need to change the data we're using to make this model more effective. And that really fits into this whole engineering process, right? We have to be able to look at the outputs, analyze them, refine the system, and do a feedback so that we can continue to improve the system. It's not going to be perfect the first time it comes out. It's a matter of what is the tolerance of the company or the government that's deploying this in the biases that it has. Have they analyzed the biases? Do they understand the biases? Have they tried to rectify issues that exist? Or are they just deploying it because it's somewhat accurate for the things that they tried and they're sold on the fact it should be good, even though it may not be? So yeah, understanding bias is a huge, huge challenge. And I think it's sort of job security for anybody in this area because, no model is accurate in reality. Some models are a good approximation of the world and some are useful, but none are truly accurate.
Really think that that's a great point using Pokemon Go, because you're talking about a game and there was no nefarious intention when developing a game. And that kind of responds to people who say there's a nefarious reason why it's identifying people incorrectly. And I think that that really speaks to and responds to that. So I think that there's just a perfect example. I really appreciate you clarifying for that. I also really appreciate you being here today. And I think we'll just wrap up. I want to say thanks again for coming in, unless there's anything that you would like to add that you feel like viewers really should know, but I think we hit most of the important parts.
Yeah, no, this is great. So thanks for inviting me.
Thank you so much. And maybe we'll have you again in the future.
Sounds great.
All right. Thank you again. This has been Dr. Derek Riley from MSOE.
Take care.
Thanks again.